Testing. Yeah, this one is a bit louder.
Okay, thank you.
I think better can let you know when.
We're ready? We're good? Okay. All right. I'm going to introduce you to a technology called fiber optic gyros for measuring rotation and supporting guidance and navigation. And I use this title because basically fiber gyros were supporting my flight and virtually any commercial flight that you take of any distance has fiber gyros on board, and optical gyros in the form of ring laser gyros also operating to get you from point A to point B safely. And they're also supporting missions to Mars, the Moon, and deep space missions. Okay, so the first question is motivation. Why would you actually go about using this technology in the first place? We'll talk a little bit about some of the markets, some of the design and development targets that are typical, how things are changing, and what the present applications are and future applications of this technology. Okay, let's start with motivation. In the early days of flight, and today, you still have the same basic problems. If you're flying along, you need to measure yaw, pitch, so yaw this way, pitch, and roll. You have to measure those three parameters. So you have to measure what's going on in three-dimensional space. You also need the velocity. So in order to get the velocity, what you have is accelerometers. You integrate the acceleration, and that gives you a velocity. So if you know the three rotation parameters and you know the velocity, you can measure point-to-point in three space blind. And so in the early days of navigation, you had things like, that's the DC-3 in the background there. But even prior to that, you were trying to do navigation, and you would do it with mechanical gyros. These are spinning mass gyros. Now, there are a whole slew of issues with spinning mass gyros, and sometimes the bearings fail, or they fail because lubricant's not right or whatever. And it turns out that you get navigation errors. Well, in the old days, if you're flying along in a prop plane and you think you're not high enough, oriented the right way, and you're not, and you fly into a mountain, it's all over. So there was a lot of accidents in the early days. And even during World War II and after World War II, about half of the delays of aircrafts taking off were due to mechanical gyro failures. They basically weren't working right, they had to be serviced. And so I can remember as a kid, I was waiting with my dad at the airport lots of times, and there'd be these hours of delays, and we'd watch other airplanes go off, but they had to replace or fix the mechanical gyro before you could take off. And gradually they got better, but these are some transitions of more sophisticated planes. The DC-3 would go on little hops. It took roughly about 6 flight segments to get from Chicago to Seattle, which is one of the flights that my dad usually took. And later you got farther distance planes that could go further, that could almost make the whole flight in one shot with the 4-engine planes. But you needed a much better navigation system than for the short flight, because the longer you're flying, these errors accumulate and you get farther and farther away from the airport. So you'd like to ideally take off from one position, say Los Angeles, and fly to New York and be within a mile of the airport. You don't want to do something like find yourself too far away from the airport, you're running low on fuel, and then you have a problem. So the requirements got stiffer and stiffer the farther you go. And then you also had the issue associated with launch vehicles. I don't know what happened to my Delta II, but anyway, this is the Saturn V. And you're basically taking off and you're going to the moon, and you're navigating primarily with mechanical gyros at this time. And there were mechanical gyros also on the Delta rocket, and I'm not quite sure what happened to the picture, but it was like the Volkswagen of rocket launches. And it launched things like the rovers, Mars rovers, the first and second generations of the GPS satellites. And if you're spending a bunch of money on a satellite, you want to put it in the right place. You don't want to put it someplace where it's going to be useless. So it's very important to make sure that you get things launched and placed positionally for rocket launches. And it's important when you have aircraft navigation, whether it's commercial or military, that you know where you're going and where you are. So there's a bunch of trade-offs with respect to mechanical gyros versus other potential types. It turns out that shortly after the invention of the laser, the Air Force was the U.S. Air Force was sufficiently annoyed that their planes are on the ground about twice as much as they'd like to. They have delays in takeoff. And they spent hundreds of millions of dollars looking at ring laser gyros as an alternative to the mechanical gyros, so you wouldn't have this delay problem. And the commercial aircraft people were commercial aircraft. The airlines were also very much on board for this, but the Air Force primarily funded it. So it turns out there's this ring laser gyro technology, which I'll describe briefly, and it's based on vacuum tubes. So it's kind of like mechanical gyros are, I don't know, Stone Age, or not quite Stone Age, but pretty close. They're like a pendulum clock. You know, some you see a few hundred years ago going back and forth, and you can still buy mechanical watches, but that's not really great. And so the ring laser gyros were a dramatic improvement. And in the 70s, roughly about 12, 14 years after the invention of laser, these things actually started to be deployed on the initial commercial aircraft. About the same time these were beginning to be ready, a new technology called fiber optic gyros came about, and this had the potential to improve things further because this is vacuum tube technology. Essentially, you're using ultra high performance vacuum tubes to tell you how you're rotating in inertial space. And again, we'll talk about that in a few minutes. The fiber optic gyros moved you from vacuum tubes into solid state. So you moved away from the issues associated with the vacuum tube technology, and you moved into a new regime where it's like moving from a vacuum tube TV or radio to one that's based on transistors. Now, this is the application space. So this is the motivation for using fiber gyros. And this is an old picture, but a lot of it is pretty relevant, even today. So there's two different types of fiber gyros. One is called an open loop or an analog fiber gyro, and they don't have quite the performance of a closed loop fiber gyro, which is for more strenuous applications, ones that demand much higher performance. So you can use some of these for stabilizing platforms. If you've got an antenna or something and you want to point it in the right direction, keep it stable, you can do that. Some oil field applications, some robotics, limited stabilization of business jets. And we were interested in ejection seats because McDonnell Douglas had modified airplanes, and if you're flying upside down in the aircraft and you eject, one of the problems that you have is that you need to turn on really fast. Now, the mechanical gyros do not turn on really fast. So if a pilot ejects upside down at low altitude, there's a 20,000 pound thrust rocket on his seat, and you will bury the pilot. 100% guaranteed you'll be in the ground by the time you're done. But if you can turn it on in milliseconds, you just have the potential at least of doing a U-turn and going vertically. So there's a bunch of issues with things, but you can do some dramatic things by using the technology. I'm going to move this over a little bit. Okay, then there's the higher performance fiber gyros. And in that case, you can talk about commercial aircraft, you can talk about military aircraft, missiles, both short and long range, as well as things like space station or, telescopes in space. So you think about all sorts of interesting applications. All right. For some reason, the difference between my PowerPoint and this PowerPoint is a little dramatic. But the point is, if you have a closed loop, and this is a circle, then what happens is you can generate clockwise and counterclockwise beams around this circle. Now, suppose the circle rotates. So it's rotating around. If you start at an initial point and the circle is moving away from that point, the clockwise beam, it will take a little longer to go around. It has to go a little bit further. But in the opposite direction, if you originate two light beams going clockwise and counterclockwise, and the circle rotates toward you, you'll have a shorter path. So the net result is, due to rotation in inertial space, you will have a longer or a shorter path that will result in a path length difference. And if you take two light beams that are very coherent, you can compare the phase between the two and make measurements that are quite precise. Actually, we're talking about milliangstrom, really, really small distance differences for some of the moderate applications where you're doing navigation across the country in a jet plane. So, this is essentially how much longer it gets. This is the rotation rate times the radius, and this is time. So that's essentially how fast you're moving times the time, and what direction you're moving times the time interval. And that's minus. So it'll get shorter and longer, and the difference gives you this difference, and that's the basic equation for an open loop fiber gyro. Okay. Now there is a way to make an improvement that's dramatic, can move you from the open loop case where you're going across fringes. And if you've ever seen an interferometer, and if you've seen a window pane, and you've got a window pane and it has a thin film on it, you'll see fringes. You'll see dark and bright fringes. What you're talking about with this kind of interferometer is you have, again, and the reason for the interference is between the back end and the front end of the oil film or whatever you have on the window, it's a very short distance. And you're looking at two beams combining either in phase or out of phase on the reflection. And the same thing happens here. You have two light beams, same wavelength, but you shift the length. You go from a bright fringe to a dark fringe and back again. And if you do nothing else, you get a sinusoidal output. But if you put a frequency shifter in the loop, so that in one direction you start with a frequency F naught, but you pick up a frequency delta F, or F in this case, you are cycling faster in one direction than in the other direction. And if you convert them both back to the same frequency when they reach this origination point, what you have is a controllable phase shifter that allows you to counterbalance the rotationally induced phase shift with an artificially induced phase shift. And when you match those two up, you get an output proportional rotation rate, but it's not limited to a cosinusoidal operation. So instead of going, well, the other approach was initially good to maybe 1 part in 1,000 or maybe 3,000. This is good to, well, easily 1 part in 10 to the 8th, and actually these days it's more like 10 to the 12th. And it's the basis for all high-performance fiber gyros. Okay, I think I've already gone through this, but this is the problem with mechanical gyros. Bearing wear, the reliability is really not wonderful, and they don't start up right away. Those are 3 of the more dramatic problems. But they had the advantage of people have been making them for decades. So there was an industrial base for mechanical gyros. For fiber optic gyros, the problem that we faced was, okay, the Air Force had dumped several $100 million into developing this ring laser gyro technology, and they had funded establishing an industrial base. So they replaced mechanical gyros for navigation, and we're competing with this new technology that is at square one. You know, we're just starting. So we were looking at, well, for the Delta rocket, which I had a picture of in my prior talk, and I thought I had one here. Basically, the guidance control people had developed a mechanical gyro-based solution for that guidance control system that was $1 million less per launch than the prior generation. A competitor's inertial system that went on the rocket. So NASA actually didn't pay for the development, but they agreed to split the difference, which meant that rather than NASA paying $1.5 million for the units, they were paying $1 million. And the other part of the agreement was if anybody else could replace that unit at a lower cost, they would be in and McDonnell Douglas would be out. So McDonnell Douglas did not want to lose $500,000 of profit for each and every launch. And they initiated this program with the electro-optics lab, and I got assigned looking at the trade-offs between ring laser gyros and fiber gyros. Okay, now it turns out that to make the ring laser gyro work, the actual preferred solution is that you actually have to shake it for reasons that maybe we'll talk a little bit about. You need ultra clean vacuum tube technology, ultra pure gases. It's a real difficult task to make these things, which is why they dumped a whole bunch of money into making it happen. For the fiber optic gyro, you get away from the vacuum tubes. It's all solid state. You can change the package geometry. And this is important because you have to go through great pains to get the ring laser gyro to work. And they have a fixed geometry. And if you change it a little bit, you almost have to start over with your fixturing and a lot of your procedures. And generally speaking, well, in fact, the leading company in this area has 2 sizes. 2. They're not going to change those 2. So to give you some idea of what's going on. They have potentially very long lifetimes. And this is an aside, but all the rovers on Mars, all the US rovers on Mars, which I think is all but maybe the Chinese one, use fiber optic gyros. And they've proven again and again they can have extraordinarily long lifetimes and they're extremely rugged. This is an old chart, but basically this is very true. They have potentially small size. They are actually very small size, and they're relatively low cost compared to the ring laser gyro for some of the modest applications in particular. For the very high end, they're about the same. So this is what a ring laser gyro looks like, or the basic block diagram. You have a gas tube, and this is helium neon, so it's a helium neon laser. It has the same kind of color as the red coming out of a laser pointer or your grocery scanner. And you have 3 mirrors. Now, when you have a laser, you need an integral number of waves around each direction. If you just go clockwise, it goes around and around this loop. So each time it hits one of these mirrors, if you don't have an integer number, the next time around, it will interfere, and it will kill the laser beam. Basically it will damp it. So the only one that's going to propagate is the one where you have some number of waves and a fixed number of waves going around this circuit. Same thing in the other direction. Theoretically, that's the ideal case, but things are not so simple. Because you have current flowing through this gas, so the current flowing through the gas, if you don't do something about symmetry, that will actually cause an imbalance. So it'll look like it's rotating, but all that's happening is the current's changing, and the flow in the current will actually make one path look different than the other. You have scattering off these mirrors, small amounts of backscatter where the light that should be going, say, this way goes back the other way, will cause the 2 laser beams in opposite directions to lock together. It's called lock-in. And it's a strong nonlinear effect. And what it does is if you don't take steps to correct for that, you'll have the same wavelengths going in both directions. They lock together and give you no information out. Because the idea is when you rotate, the integral number is going to have to stretch, the wavelength is going to have to stretch and become longer in one direction and shorter in the other. The net result is a frequency difference between the 2 beams. And that gives you your possibility of doing a readout. Anyway, to solve the current problem, you need symmetrical anodes to have the current exactly balanced, and you have to take some measures to make sure the current really is balanced. If anything happens to cause this thing to be asymmetric, you're going to have a rotation error. That's really a current error. So you're beginning to see some of the problems. The readout unit, well, let me back up. Out of the surface of this one mirror, this is partially transmitting. The way you actually set this up is you have the 2 beams come out of that partially transmitted mirror. You have an angled prism, and you have 2 light beams at slightly different frequencies interfering on a split detector. This causes an interference pattern to move across that split detector, and it's like you have bright and dark fringes, and as they roll across, you count how many counts up, how many counts down, and that turns out to be a counting angle. So you're counting how far you've rotated this way or that way just by keeping track of the counts and which way they're going. Are they going clockwise direction or counterclockwise? Okay, I apologize for the graphics somehow getting messed up. But basically the idea is you have a light source and the open loop fiber gyro, and instead of having a cavity, you have a fiber coil. So the fiber coil is sitting here, and you generate clockwise and counterclockwise beams that traverse this fiber coil. And this fiber coil could be 100 meters, it can be 3, 4, 5 kilometers. So it can be very long. And what that means is you can generate a significant time delay. So when you rotate this coil, you rotate it through so many degrees or an angle, and that corresponds to a path length change. Well, the rotation rate times the time delay gives you a path length change that's much bigger than a ring laser gyro. Instead of going one time around, you go many times around. And the idea is you have to ensure that the light beam going clockwise and counterclockwise through that fiber coil are exactly matched. And to do that, you have to go through a number of exercises, and it turns out that you need 2 beam splitters and a polarizer in the center. So this is essentially extra devices to make sure that you traverse the exact same path. Because if there's a slightly different path going clockwise than counterclockwise, even by a tiny amount, again, for inertial navigation flying across the US, you're talking about a milliangstrom. And so if, for example, the polarization going this way is not quite the same as the other way, and both beams do not see small perturbations in that coil, that will be a big error. So the open loop fiber gyro does that, but it doesn't counterbalance rotationally induced phase shift versus frequency induced phase shift, which is what this does. So rotationally induced phase shifts are counterbalanced by frequency induced phase shifts, and that gives you the wide dynamic range. All right. There are additional issues, one of which is that if you look at, these are equations, but this is rotation. That's your rotational output. And for the closed loop fiber gyro, you have a frequency output, which you can actually convert to a readout unit that has the same counting feature as the ring laser gyro. It counts up, it counts down. But if the wavelength of the light source changes, that means that the proportionality factor between this count and the rotation rate shifts slightly due to wavelength. So you have to be careful about how you select your light source, how you stabilize it, or you measure the wavelength to be able to compensate for that, for both open loop and closed loop, but it's important for both. And this is just showing how you do it. And I'm going to skip some of these messed up graphics and go to pictures. So this is the first closed loop fiber gyro, built in 1978. And it's got 100 meters of fiber on a big spool. The platform underneath it is roughly a meter on each side, so it's a meter by a meter. And initially, we were using a helium neon laser. So it comes through some steering optics, and there's light that goes clockwise and counterclockwise through this loop. There's a frequency shifter right there in this holder, and this whole thing is sitting on a table, and the 2 beams are combined on this detector sitting over here. To give you an idea how bad this was, I mean, this is sitting on a plate. You've got all these optical components moving around, and you're spinning this table, but we can only do it about 30 degrees a second, because any faster than that, we panicked with respect to the cabling. And the low end was about half a degree a second, or 1,800 degrees an hour. That's a big number. It's a huge number, but it showed that the principle worked, and we basically demonstrated it, and we patented the approach. We filed the patent in December 7th of 78. But the Delta rocket people were looking at this going like, okay, this is never going to fit in our inertial package. You have to make it smaller. So we designed the first solid state fiber gyro. That one had a gas helium neon laser. So this is 5 inches or 12.5 centimeters in diameter, and it's 1 inch or 2.5 centimeters thick. And it has, again, 100 meters of fiber. The helium neon laser is replaced by one of the first laser diodes that Hitachi ever made. And that little package there in $1979, in $1979 was $3,000. The same thing you can buy for 50 cents today, yeah, in today's dollars. So it's probably equivalent of, it's ridiculous how much the price has gone down. In any case, the light comes out of here, it's columnated, and there's a beam splitter to generate a beam that goes through the frequency shifter counterclockwise, and the other way it goes directly into this other end of the fiber and goes around this way. This is extremely difficult to align because at that time there were no fiber connectors, and the diameter of the fiber is about 125 microns, but the core was 4 microns. And we had to be aligned to about this and assemble it and get it all to work. But the last little trick is there are some steering wedges in here. Essentially you have wedge optics, and so the last little alignment you'd have to turn these little screws to get things aligned properly to get the high throughput. And that's historical, but the point is it was not easy to build. And the killer was that we were running tests. We finally have this thing completely running. And that little $3,000 diode lasted half an hour. And we got some data. And it turned out that it moved into an LED mode. And shockingly enough, even though the power had dropped dramatically, the signal-to-noise ratio was the same. And it was like, what is happening? Well, there's a thing called coherence length. And what coherence length is if you have a light source that emits a very, very narrow band of light, you can have path length differences that are large, and the beams will interfere and give you a good signal. But if it's very, very short, then you have to have those two path lengths matched very closely before you get a good signal. So what was happening, and there's many, many problems associated with how to build a fiber gyro, but what was happening is the long coherence length laser diode, when this is operating the way it was supposed to, scatters small amounts off the optical fiber backwards. And that backscatter, if it has a long coherence length, say 100 meters, would be scattering off the entire length of the coil backwards, generating a bunch of noise. So we had higher power, but the backscatter caused noise that essentially matched the advantage you had with respect to higher power. And when it went down from about a milliwatt of power to maybe about 20 microwatts, something like that, everything scaled down. So we never ever used an expensive light source. The LEDs were much cheaper. Yeah. So the year after, we built something smaller in 1980 because they were not satisfied with 12.5 millimeters or 12.5 centimeters. And so we're down to 6.3 or something centimeters. And we folded this all together, made some improvements, so this smaller unit actually worked better than the 5-inch diameter unit. But it's all glued down, so we developed some pretty expensive equipment to be able to do that placement effectively. But we still haven't built anything that could be put in the field. So we built another version of this for another aerospace application where we demonstrated you could, instead of having the coil being circular, we built a racetrack type one. So it was a long, elongated device. And an oil company came in, an oil service company, looked at the racetrack and went, we've got to have this. We want to put this, essentially what you want to do is you want to navigate while drilling. And why would you want to do that? Well, there are oil leases essentially sold, for example, in the Gulf of Mexico. And you have tracts of area of the Gulf of Mexico which an oil company may buy for some outrageous amount of money, maybe $1 billion, $2 billion, whatever it is. And another oil company has an adjacent lease right next to yours. And you can, of course, go down with your oil well, and you can go sideways. And what you want to do is access possibly the same pool of oil as your neighbor, but if you go into their territory, the powers that be make you fill in your entire drill string of effort and seal it. Well, the oil platforms cost about $2 million a day to rent. To give you some idea of the money that's floating around here. And they asked us to look at building a tool that could actually do the navigation features. In order to do this, we needed a 10th degree an hour gyro. They wanted to do gyro compassing. Okay, I need to explain why you want to do that. Prior to being able to do this kind of navigation with a fiber gyro, they were using a magnetic flux gate. So it's like magnetic fields, and now that magnetic fields can deviate, they have a whole bunch of problems with anomalies in the Earth and whether you're getting true north or not. But ignoring that for the time being, they had to use a non-magnetic drill collar in that vicinity of the magnetic flux measurement device. The unfortunate thing is that did not have the material strength to avoid snapping periodically. And if you want to really annoy your oil company that's spending $2 million a day, and he's got a drill string going way down, and it breaks because of the weak link of your non-magnetic drill collar, you have to pull the whole thing up and put it down, and you've lost like $1 million. And their solution is, well, okay, we take it up, we replace it, we send it down again. Maybe the sensor costs $300,000-400,000, but we'll just drill through it and be really mad at the guys that supplied it. So in this case, when you're measuring Earth rotation rate, you're just trying to gyro compass by measuring the components of Earth rotation rate, there's no problem. You use the conventional high-strength steel, which would shield the magnetic field, drill collar, and you're safe. Anyway, we built one of these in 1982, and this is one of the first models sitting at a show in Houston, circulating around, showing that it could actually have sufficient accuracy to tell you which way you're drilling. The problem was the oil market, which was very high, crashed. So anyway, things got abandoned, but we did have a very interesting gyro. Here you can see the racetrack coils on both sides. The electronics went into another section of the tube, so it could be very long. The length was not the limitation, but it had to fit within the drill string, which was like something on the order of 4 or 5 centimeters in diameter. About the same time frame, in 1983, we started to build the first fiber gyros used on jets. This is for a business jet application. And all that we were doing was demonstrating that it could be used to stabilize the plane. So as you're flying along, you have the navigation function, but you also have the problem that the wings are bouncing around and so on. But you can correct for that if you had what's called an attitude heading reference sensor, which is what this was. And it just keeps your plane from jostling. So that's 1983 with the open loop case, which is okay for that application. And for the Air Force, For Eglin Air Force Base, we're building some more sophisticated closed-loop versions that we delivered. So that's 83, and this is 1986, where we're incorporating some of the lessons learned from the oil drilling tool into a better unit for Eglin Air Force Base. Well, at this point, McDonnell Douglas had won every single Air Force contract that had been awarded. There weren't big contracts, but they were everything that existed. And we were annoying the competition in the US because we had the fundamental patent. They were unhappy that they wanted to be the McDonnell Douglas suppliers, and eventually McDonnell Douglas went fine and licensed anybody to go ahead and use the technology we developed. So it really transitioned to companies worldwide. Literally, companies were licensed in the US, in Europe, and in, well, Japan. And it was probably the right thing to do because we had a core element of the technology, but we didn't have everything. We did not have a chip that could basically do all the functions that we needed to have as far as beam splitting and frequency shifting, or in fact phase compensation, all in one little package. And there were other companies that had developed. So there was a bunch of patent swapping going on to enable, companies in Europe and US and Japan to all be able to do this. Okay, so that's essentially showing what this is, but it's pretty simple. In principle, you've got, well, here's a coil, and there's this integrated optic chip, which has the polarization function, the beam splitting function, the modulation functions, the frequency shifting functions, all on one chip. And everything else is pretty much the same. So if you look at kind of a timeline of what happened from the late 70s, well, 76, 77, to maybe around 86 or 7. So you have roughly about a 10-year window where there were early hardware demonstrations, and we were very focused on trying to get into real applications. So we were building some of the first real hardware, the first things that actually got demonstrated. Other people were looking hard at what are the fundamental physics limitations. So national labs in the US and universities and companies that were doing inertial navigation and wanted to move into this field were all looking at this very intensely. So when we licensed this, they had our technology plus all the things that they've been doing for the same period of time. And these are some of the companies that basically took what we had and what they had, put it together, and moved it toward products. So in Europe, there's Photonetics, which is now IX Blue, and SEL, Alcatel, which is now Safran, and Litef, which is a subsidiary of Northrop Grumman, which is a US company that actually dominates the market. So in the US, it was Litton and Honeywell, and in Japan, Hitachi, Japan Aviation Electronics, and Mitsubishi. So moving a little bit farther through the 1990s toward 97, 99, the technology moved to the point where Mitsubishi actually used on lunar and Mars missions fiber gyros for the navigation solution. So we went from, the initial brass board demo was 1,800 degrees an hour. we moved to roughly about maybe 100 degrees an hour, so maybe a factor of 20 better on the solid state versions for 1980, 82, until we did the gyro compass thing, but we sort of had to mechanically 1990. So a 10th degree an hour versus 1800 degrees an hour is already a factor of 18,000. And then by the time you get to what you needed for this, you've got another order of magnitude, so it's a part in 180,000 comparison. I mean, you've got this, you're starting to move orders of magnitude further and further up the chain. So this is the first real product that Northrop Grumman came out of. It was originally Lytton, but Northrop Grumman bought it. This is a 3-axis fiber gyro package, and it's designed for 1 degree an hour. And it's used on a fairly wide range of platforms. The rovers use something like this version or one that's a little better, depending on what year it was launched. But they can also be used for aircraft stabilization, short-range aircraft, or missiles. This is an aircraft navigator on the left, and this is what the Air Force would put on, or a commercial plane, and this is what the Army would use for their inertial navigation of high-value land vehicles. This is Honeywell's version. They were one of the first to actually put these things on commercial aircraft. They used it as the, for safety, when you have a commercial aircraft, there's no ejection seat, right? So you want to have the absolute maximum possible safety you can on a commercial aircraft, and you want to avoid any failure mechanisms. So it turns out that one of the ways you do that is you build in redundancy. So if you have a ring laser gyro as your primary navigator, you might have an extra axis to make it a little bit more robust. But if you use a different technology, like the fiber gyro, in addition to the ring laser gyro, it turns out that you have another safety factor on top of that. So starting with the 777, you had both the ring laser gyro and you had the fiber gyro acting as navigators at the same time. And that's pretty much baseline now. If you have a fighter aircraft, because of weight and power constraints, they might say, hey, we're just going to do one or the other. So an F-16 uses fiber gyros as its baseline navigator, and you might have another military aircraft that uses a ring laser gyro system. In any case, there's a couple of, I should check, I'm going over time, I think, before too long. So I'll skip some of this, but there's different types of fiber that give you different performance. It turns out that you can have certain solutions that are relatively low cost and others that are very expensive. And Honeywell was looking at a lower cost solution, maybe giving away some performance. But in any case, there's alternatives there. This is what the packages for Honeywell look like for the really high performance inertial navigation. I'll show you a few other slides here since the pictures are turning out well. This is basically making fiber. You take a tube and you have ultra-pure gaseous glass that you flow through this tube, and as the gaseous glass cools down, it builds up on the inside of the tube. And when you get toward the core area, you dope it with some material, typically germanium, but there's other materials, and you have a higher index of refraction in the middle of the fiber than at the edges. And that actually traps the light in the center of the fiber. So after you make this tube, you collapse it down, you take it to a draw tower, which is usually about 5 meters high, and you melt the end of this rod, and you draw it down to whatever diameter you want, and you coat it with whatever you want, and you reel it in, and you can make many, many kilometers of this kind of fiber. So I'm probably going to skip some things here. Well, maybe I shouldn't. Anyway, it turns out you can have the side neck interferometer, which is what the fiber gyro is based on, make an acoustic sensor. It turns out that if you have an acoustic wave hit offset from the center of the coil, it would be acoustically sensitive. So in order to circumvent that, you can take the coil and wind it from the middle so that both ends are symmetric, and people have gone through great perturbations on how to do that. And I'm going to skip all that. And maybe you can have open loop gyros with fancier digital processing these days and get the cost down. They still don't work as well as the closed loop ones, but they're better than the early days. There's been progress made there. And I'm going to skip that and just show you, this is a US quarter, maybe about that size, and that's electronics, optics, and everything in something about that size. And you can put it in packages, and they're used for stabilization of imaging from like helicopters. They can be used in drones. DARPA, which is the Defense Advanced Research Project Agency, sponsors a robotic race across part of the Mojave every year. And KVH, which is the guys that make these open loop fiber gyros, has about half the robots in the race use their technology. So it doesn't have to be that great, but it has to be pretty good to make sure that the robot actually goes scooting across the Mojave and arrives where it's supposed to go. And they also had the winner of that race, that's what's shown there. And undersea vehicles, as well as military vehicles. Okay, and I'm going to skip the Japanese versions. I'm going to mention this, though. So I talked about the requirement from flying across the U.S. or maybe from New York to London being about 0.01 degree an hour. You can also take off from Los Angeles and go to Shanghai in about 12 days. And if you want to be within a mile of that airport over that 12-day period, you need a way better navigator. And on the open ocean, there's a lot of segments where GPS is not available. So in order to do that, you don't need 0.01 degree an hour. You need 0.00001 degree an hour. And that's now doable with a fiber gyro, and you can't do that equivalent with a ring laser gyro. So if you need super high performance, you pretty much need to go to a fiber gyro. So continuing on, all the rovers have fiber gyros on them, and those gyros are also used for the 7 minutes of terror when you're navigating to land the things on Mars. Lots of satellites and deep space probes and so on. And what else have I got? And I think and this is how it's ballooned as far as how many of these there are. There's over 1 million worldwide, and that's not counting whatever China and India and some other countries have built. So it's growing to greater and greater numbers. There are some competitions. On the low-end market, there used to be fiber gyros built for automobiles, for navigators, but there's little vibrating beam ones that are used in the mice for computers, that are good enough with GPS for your automobile. So that took over that market. And on the very high end, there is, this is the MEMS-based devices with little vibrating beams. On the very high end, there's a thing called a hemispherical resonator gyro, which is super accurate, and you can buy it for maybe around $200,000-$300,000. So it's not cheap. In fact, it's quite expensive. But to give you maybe a reference point, the rockets that place the James Webb Telescope where it is are usually, well, almost all the rockets are now fiber optic gyro navigation systems. But on the James Webb Telescope, which is a mere $10 billion project, there's one of these hemispherical resonator gyros for, long duration, super high accuracy and stability. So there's competition and new technologies coming along. And that should be, I'm going to skip the derivative stuff because we haven't got time. There are many derivative inventions that you can use for intrusion sensing and distributed acoustic sensing for figuring out where bugs are in grain silos and if somebody's intruding on your territory. This is a list of references. Some of these are conferences. Historically, the earliest one is '82, and then I started 10th, 15th, 20th, so on, anniversary Fiber Gyro Conference. And for the 40th anniversary, I came out with this book on design and development of fiber gyros. This is essentially embellished, extended papers into chapters that tells you what the state-of-the-art of fiber gyros are. And if you really want to know the gory details, so this is kind of the more practical side of things. The theoretical baseline physics is Hervé Lefebvre, he was the past president of the European Optical Society, and he's been involved in this as long as I have, which is 45 years on and off. This book, The Fiber Gyroscope, is really the definitive book that describes it all. And I'm going to stop here because I think I've gone about an hour. Are there any questions? Yeah.
What were Russians using in their spacecraft?
The question is, what are the Russians using in their spacecraft? Well, interestingly enough, we were selling the Russians fiber gyro systems. So I'm not exactly sure what they have used, but the Russians actually have one of the major suppliers of open loop fiber gyros. It's called Optica. And they also have closed loop fiber gyros. So I don't know whether they're using their own domestic suppliers or US suppliers, but they may have been, I don't know, I guess is the fair answer. They could have used either one. But I think they were farther behind, I think they're definitely farther behind than the free world fiber gyro suppliers, but there are restrictions on what you can export for obvious reasons. You don't want missiles flying in your direction that you have more accuracy than yours going in the other direction, and it's a problem. Yeah. So, yes. Yes. Yes.
So I think the technologies come pretty much cheaper and affordable in the last years.
Yes, and I neglected to mention India. So there's three countries. There's Russia, there's China, there's India. And they all have good technologists and research and development capabilities. And they're all capable to varying degrees of doing production. So yes, I think everybody in the space race for their launch vehicles is probably pretty much zeroed in on fiber gyros for launch vehicles, and probably for satellites as well, or missions to other planets. So we'll probably all be using the same technology, I think. As far as the super high performance spherical hemispheric gyro, I don't know if they have that technology or not. The only two that I know of are Northrop Grumman and Safran. Those are the only two that I know about. There may be somebody else out there, but yeah. Okay, well, I should hand it off now. Thanks very much.
energy system and novel architectures in our crates. We are doing really, really close cooperation with the companies, not just in the area, but also in national and international level. And pretty much everything what we do within the research projects with companies. So I think that there isn't a research project in WEBIC which does not include companies. So we have research program managers, we have project managers, but then we are doing really close cooperation with the professors in academic units and their research teams. So basically they're professors in the internal combustion engine lab and smart grid and flexible energy resources lab, and also coming also from the business side, because we are combining technology with the business and with the societal issues, because energy transition is a multidisciplinary challenge, and this kind of requires this kind of system level thinking, and it is not discipline based, so we have to combine different kinds of perspectives to actually manage this kind of system view, what we need to have when we're dealing about energy transition. This is just briefly what we are doing and what kind of research is included and activated. So we are doing research on low CO2 emission integrated energy systems, and especially what comes to the power plant, internal combustion engine power plants, and alternative fuels, gaseous fuels, smart grids, flexible energy resources. And what comes to smart grids, there is this, of course, this kind of idea of resilience and cybersecurity, because smart grids, it's about data. Then it has to be somehow, there has to be the cybersecurity aspect and the resilience aspect also. Flexible energy resources, whatever is integrated into the grid via inverter, different kind of energy resources, renewable energy, electricity production technologies, how we are integrating them into the grid, and of course how we are integrating storage in the future, batteries, but also, for example, hydrogen, because they will all be connected to electricity grid. And then, of course, the business side. How will the market, what kind of changes there is needed in the market? What kind of new opportunities? But then again, we are talking about energy, which is highly regulated. So what kind of differences we actually need in the regulation and the legislation to go forward? Because this is not just technological problem, it is also a societal challenge what comes with energy. Because when we are talking about energy and economics, they are like two sides of the same coin. They are so intertwined. And we are actually seeing it now in these really, really unfortunate circumstances when we are having a war. And now we are seeing what kind of connection there is between energy and economy. So, my perspective comes from energy, and especially what comes to the renewable electricity production and how we are seeing the future energy system evolving and what is the role of photonics. So my driver is climate change. And it's a huge driver, it's a very important driver, and some kind of driver that we can't just not see, because we are seeing this kind of results of the climate change already during this summer in the southern and middle Europe. Just to remind you about the decarbonization and what kind of requirements there is if we want to kind of reach this 1.5 degree increase in the global average temperature agreed in the Paris Agreement. Well, if we would like to go there, it means that the decarbonization rate should be 12.9% in a year annually at the end of the century. And right now, we are doing pretty much here. 2.5% in a year. There's a huge gap. And if we want to actually go forward with the 2%, we are going forward with the 2 degrees increase, and we are allowing that. Even that is a challenge right now with the actions we are doing now. So, this is my future, this is my playground, and our researchers and professors' playground. This is a vision from European Commission. It's called the EDIPS Net Network, where we are actively taking part of the working groups. So we are trying to, in a way, have some kind of impact in the EU level, how we are building these visions for the future energy systems. So it's quite complex, and it will be a bit more complex what we are having now, the energy system. We will have delocalized energy production, and there is already a role in the photonics in energy production, because photovoltaics is about photonics. Solar cells, they are photonics. We are actually measuring how these power plants are operating, how they are aging and the materials are aging. We are already censoring them and measuring them via photonics. It's really important not just to produce electricity, but also to measure how we measure. Because right now, usually when we're talking about photonics, we are thinking about, okay, telecommunications. We had the hype in early 2000. That's right. Or computing, quantum computing. But then again, it is important to have the data, yes, and to be able to actually compute the data, huge amount of it, because this is managed by data. But how we sense, how we measure, it's as important as the data. We should have quality measurements, and we should have good enough data. So actually what kind of sensing we are using is really important. And there is also a role for the photonics in the future. Because like I said, this is about sector coupling. We are seeing electricity grid coupling with thermal networks, coupling with gaseous grids, coupling with storage technologies, batteries, hydrogen. So to manage this kind of system, it needs data, and it needs censoring, real quality data, produced with right censoring, produced with quality enough measurements. And then the other hot potato in the future, I'm talking about batteries. And then we have to talk about critical materials and where they are coming from and how they are produced and from which materials. So, rare earth materials, they are really important for the energy transition. Not just for batteries, because we are using them also in the magnets, and that concerns wind generators and wind power plants, electronics, lighting. So they are really, really crucial. And also in steel production, we need rare earth materials. And so you can see here in the right where we actually produce the material and where we process the materials. I can be very proud here, yeah, Finland is mentioned over here in the cobalt side, but then again, there is quite much mentioning in the coming from China. EV battery business is 27 billion business. 10 out of the most biggest EV battery manufacturers are coming from Asia. Most of them are from China, but there are couple from South Korea and Japan. And this is something, because now we have to think about, we are in the situation where we are actually thinking about where our energy is coming from, where we are purchasing the energy, how the energy is produced. But we have to also think about, all right, where the battery materials are coming. So how we actually use photonics in here. Because if the transportation is going to be electrified in a way that it has been assumed in the visions and in a way that it is actually showing right now from the statistics, it means that we actually will have to recycle the materials. There will not be enough if we don't recycle, or if we don't figure out some other replaceable materials for them. So when we're talking about recycling battery materials, then we are talking about photonics, because we are talking about spectroscopy and, for example, photonics in the spectroscopy. And where we use it, we actually use it to identify the materials, because when you recycle, you have to identify the materials. And then you have to actually, when you are using and producing the cells, the battery cells, then you have to actually be able to measure the quality of the material, because the materials, they age. And the battery, when it's working, it's charging, and there is these cycles, it actually ages. And you can actually measure it with laser spectroscopy, for example. And then you can actually, you can control the manufacturing system with laser spectroscopy, which is photonics. So you actually can control that the structure of the cells, it is what it should be, and the process, and they are operating in a way that they should be operating. So it's about safety, but it's also about recycling and the ability to recycle these materials. There we need photonics, and this is crucial. So there is huge possibilities for photonics in the field of energy, because, for example, this here, this is critical when we are talking about energy system, which is a critical infrastructure, and how we are actually managing our own energy system, not just in Finland or in the Nordic countries, but in the EU area in general. So, thank you.
Okay, thank you. Do we have any questions for Suvi or Erik? Or Sami?
Yeah, I was just asking if you considered maybe a hydro storage area where you'd have a high area and pump the water up and go that way.
Not necessarily in Finland. I think that these kind of solutions, they are more used in Middle Europe, where they have this kind of more height and variation in height, but also in Norway.
Oh, could you do it in Sweden?
I don't know if they have done it. I don't know if they have actually done it, but usually it is it's a solution used in the Middle Europe, and not necessarily in here. But then again, of course, you can do it, and we have hydropower. So in a way that we can do it, but then again, is it this kind of good choice to do here in Finland? Because you need a bit height.
Not too long ago, I found this very interesting subject of thermoacoustics. in form of YouTube videos where they were using them for propulsion of some small, very light craft, or just to separate the air that was mixed by entropy into, well, in a tube into a hot and a cold place. Are you considering any of those technologies?
Not at the moment. I can say no, not at the moment. Yeah.
All right. I think this wraps up our session tonight. I hope you have had a fruitful and learning experience here, and you can by all means continue the discussion here. We still have some sandwiches, some beverages, some cookies, and great company. And below, and there is some candy as well. And in the first floor, Culture 3.0 is starting. Pierluigi Sacco from Italy has flown all the way here, and he is taking the floor in about 2 minutes. Maybe Sture has already started, so you can grab something on the way there, as you like. But thank you.